here when the power went out. Okay. So we are looking at, I should hand you these quadratic functions. What that means is that we are talking about things related to x squared. Which is good news because we already know a lot of stuff about x squared. Like I said, we're going to get into a lot more detail, of course. I'll just say related to y equals x squared. A big part of the reason that we care about quadratics is because they show up in all kinds of places in the sort of world around us, and in particular in projectile motion. Like the way gravity works is quadratic, excuse me. So we'll do some modeling. We'll probably look at some on Thursday where we've got a quadratic that's like modeling an object moving from the air through the air as it's sort of being pulled back down by gravity. But really, anytime you look at something where you're like throwing something into the air, or an apple falls out of a tree, somebody hits a ball, whatever, it's all kind of fitting into the same scenario. So hang on, drop basket. There we go. Backboard. So like the actual path of the ball here is quadratic, right? So the graph, the shape of this thing is basically going to be the same shape as the graph of y equals x squared. Right, we'll come back to that in a second. But now there are a couple of like modifications that we can make in like the real world about like how wind affects things and that kind of thing. We're not really going to get into that, but the basic idea is that works. Galileo was actually one of the first to really like get into the details here. And I think this is cool. So I'm going to talk about it for 30 seconds because it's my class. Galileo, like mid 16th century, right? So he's like dropping things and timing how long it takes to figure out, from different heights how this works. And he ends up building this like long wooden track to do it. He's dropping balls down and timing it. But the problem is timing things when you don't have clocks, really. You have like hourglasses and maybe a thing that would tell you what hour it is or something, but they don't really have clocks. So the way he timed things was he would hum the same tune to himself and keep track of the beat, because he was enough of a musician that he had good enough rhythm that he could do that. I don't know, I think that's cool. You probably don't care, that's fine too. Quadratics, stuff related to x squared. So let's talk about x squared for a second. I said it was going to take 30 seconds. I pretty much stuck to it. History of math coming your way, spring 23. Y equals x squared, we know looks like this. So nice kind of smooth U-shaped graph, sort of, right? We've been working with it for a while. A couple of times I've probably slipped and called it a parabola. That is the name of that shape. So we're a little further along. We're a little more matured in our approach to the class. I'm going to start using some of the math words that we've been dancing around. So that's the name of that shape, is a parabola. If we're thinking about sort of reading it left to right, we know it's domain and range also, right? X values where that thing is defined. Everywhere, right? What about the range? Just the upper half, 0 to infinity. Okay, that's probably kind of a good thing to keep in mind as we look at a sort of broader class of like things that look like this. The domain's always going to work the same way. They're nice, they're friendly, they're defined everywhere, they're continuous everywhere. We don't have to worry about that so much right now. Range is always going to be some kind of like I'm doing air quotes, half infinite thing, where it's either like from here up to positive infinity, or if it opened the other way, then from like from negative infinity up to some sort of cap, right? So it's always kind of a half infinite thing like that. If we think about like reading the graph left to right, or, think about like a roller coaster track or something. Here we are, as you move left to right, the y values are decreasing, right? So this function is decreasing, it's headed down until you get to this point where it sort of stops for a second, turns around, and then starts heading back up, right? So this point that's different than the others, which is the same point that we've been keeping track of to like move them around and do all the transformation stuff. It's a 0, 0 on this one. That's called the vertex. Again, I've probably said vertex a few times, but now, officially, that's the name of that point. Okay. And the only other like terminology stuff that we need is that this parabola has, this one in particular is an even function, but anything that has that same shape, the two sides of it relative to the vertex look like mirror images of each other, right? This side and this side, because of the way the function works, these two sides of the thing look identical to each other, just going in opposite directions. So basically the center of the thing, where the vertex is, that acts kind of like a mirror. So the vertical line that passes through that, excuse me, we call the axis of symmetry. It's a vertical line. This one would be, what's the vertical line that goes through the origin? How do you write the equation for a vertical line? Y equals 0 would give you all of the points. Think about like a table of points. What would they all have in common? Whatever the x value is, the y value would be 0. If you plot all those, what do you get?
It's going to be, it'd be x.
Horizontally, yeah. So for a vertical line, we want the other thing to happen. X equals 0. So y equals always gives you a horizontal line. X equals always gives you a vertical line. This is a line. So when we talk about an axis of symmetry, and there are a couple other places this semester where this will come up. Anytime we're talking about a line, we should be using an equation to talk about it. So just saying 0, that doesn't mean anything. Like, what's the axis of symmetry? It's 0. 0 what? Like, I don't that doesn't tell me anything. So it's x equals 0. Again, there are a few other places that'll come up. So I'm gonna, kind of seem like I'm being a little nitpicky about things, but there's a reason. Oh, and be advised on the same kind of topic, MML stuff. It always wants an equation for the axis of symmetry because it's an equation of a line. Sometimes it does the thing where it gives you x equals and just has a box where you type your answer in. Sometimes it does the thing where you just have a box and you type the whole thing in. I know that's annoying because sometimes you're going to get stuff counted off because you like typed too, like you entered too much, right? Like if you put it in x equals 0 or something, it's probably going to count that wrong. I'm fine if you want to, email me if this happens, and I'll, go in and change it if you don't want to rework the problem or whatever, that's fine. But it is the equation of a line. I know that math on the computer is annoying. I get that. Sorry. It is an equation though, so we want to be careful that we're talking about it with language that really expresses that. Okay, so that's terminology stuff. Everybody good so far? All right. So for like this, the vertex is right here. So the axis of symmetry would be, right there, right? So it's not that it's the y-axis, for y equals x squared, it happens to be the y-axis, but that axis of symmetry moves along with it, right? Okay. So let's take a look at an example here. This is the first one about halfway down the page on the notes. Suppose that f of x is negative quantity x minus 2 squared minus 3. We want to find the vertex, the axis of symmetry, the domain and range, and then rewrite the function in standard form. All of this is stuff that we know how to do already. Now that we've talked about what those words mean, what the words vertex and the phrase axis of symmetry mean, you know how to do all this already. Treat this just like you would have done seeing a question like this show up on the test yesterday. If I told you to, sketch that graph or figure out how that's different than x squared, what would you do? What does this look like?
It's a parabola,
It's a parabola.
and it's upside down.
It's upside down because that negative out in front reflects over the y or the x-axis. Shifted to the right 2 and shifted down 3. Okay, so if you start with x squared, vertex at the origin, you go right 2, upside down, down 3, figure out where all this stuff ends up.
294 here.
Okay, so we've got a quadratic, so the graph's a parabola. Starting with x squared, this is shifted to the right 2, reflected over the x-axis, so it's opening down, and then down 3. Stuff we want to sort of get into the habit of doing and looking for right away, like right off the bat. One, of course, is like, what kind of function is it? For the time being, we're kind of just going to be talking about one thing for a little bit, but we want to be thinking about that, like, how do I recognize that? And then also stuff like that. If it's written in such a way that I can just pick those things out real quick, then, at this point, we should be pretty good at that, kind of identifying that kind of stuff. That helps to think about, right? Right 2, down 3, upside down. Stuff I want to be sort of training myself on and thinking about is that, okay, if this is an x squared, then the graph looks like that, right? So it's a parabola. And if there's a negative out in front of the whole thing, so the negative, the like leading term is negative, the biggest thing, the x squared is negative. What does that tell us about the graph? That it opens down. And I'm gonna, be doing this kind of thing with my hand basically all the time. If you are at all, tactile, kinesthetic or whatever, I would, do the same thing. A lot of the stuff that we're gonna need to know comes down to knowing like just a couple of pretty basic things about the function, like where is it and which way is it facing? If you can, if you want to think about like application type stuff, we're dealing with either a parabola that opens up like that, which means it has a minimum value, or one that looks like that, which means it has a maximum value, right? So thinking about applications, finding a maximum or finding a minimum, that's pretty important a lot of times because we might be trying to, sort of do something in the best way, right? Okay, so anyway, all that in mind, where is this one? What's the vertex here? 2, -3. Again, just a reminder, the vertex is a point, right? So it's an XY pair, it's coordinates. Okay, so whatever the details look like, there's just a little sketch. This thing opens down and its vertex is 2, -3, right? Again, that, that kind of thinking about it is going to help us figure out where to go pretty often, I think. What about the axis of symmetry? X equals 2. It is the vertical line that goes through the vertex. So those two things are always tied together, like they have to be. The vertex works like the middle of the parabola. Axis of symmetry is just a line through the middle. So those are tied together. How about domain and range? Yep, domain is the whole real line. Is what? Negative. So why -7? Where's -7 coming from? Oh, I see. So it does pass through -7, right? That's the y-intercept. There's the vertex. It keeps going though, right? So when we talk about range, we're talking about all the y values that it covers, right? So should like -40 be in the range? Yeah, and negative, and both ends are, pointing down, right? It's continuing on, right? I could do this all day. We're at, -60,000 or something now. I still see it, continuing on. So, Ash? So negative infinity for sure, because the ends are pointing down.
I lied, it would be -3.
Because it's opening down, this has a cap, right? It's got a highest point. That highest point is right here. We're talking range, so we want the y values. So negative infinity to -3. This doesn't go any higher than -3, but it does get to -3.
Would that be the other way around if it was, say, instead of it being negative, it would be positive?
Yeah, so if it was in like the same place but opening up, it would be -3 to infinity. Yeah. Yeah, so again, the range part, it's always going to be like a half infinite kind of thing, either negative infinity up to the maximum or from the minimum up to a positive infinity.
So wait, since it's negative, like this, since the parabola is negative, that means you write the range backwards, or it's just.
We're not writing it backwards.
Sorry, I mean like the negative infinity to the number.
Yeah, yeah, right. If it's opening up, it's going to be, whatever this is, up toward positive infinity. If it's opening down, it's going to be, because the ends are pointing down, negative infinity is this way, right? So it's everything up to wherever this is.
Okay.
Yeah. All right. Now this part about rewriting. What we're trying to do is take this and rewrite it in what we call the standard form, which if you look, I wish I didn't have to keep scrolling back and forth. Looks like this. We'll talk some more about like why and when we use these two things in a minute here, but y equals ax squared plus bx plus c. Really all we're trying to do to rewrite this is just do the stuff that's already sort of spelled out here, right? So negative quantity x minus 2 squared minus 3. This is a little bit of an artificial way to write this, but we do it because it tells us, where the vertex is. So this thing actually even gets called sometimes the vertex form. That's what we're going to call it, because you can look at it and you can tell where the vertex is, right? Which is nice. It's convenient. It makes some other stuff kind of clunky and weird though. So we're also going to look at stuff that's written in what we call standard form, which we get by just expanding all this out. So first I want to do the square there, x minus 2 squared. Which again means multiply it by itself. So when you do that, FOIL or distribute everything, x times x, x times -2, -2 times x, -2 times -2. All right, I'm expanding that. Then we can combine those. Distribute. And then finally, combine like terms. My son yesterday was working on his little like preschool like book thing and had had little like dotted outlines of numbers, and so he's tracing all his numbers and stuff. He's like having fun, doing great. He got to 7 and he traced the 7. And he was like, I think I'm gonna cross my 7. And then they did. I was like, yes you are. Good job, bud. Because he's seen me do it. He's like, why do you do that? I'm like, so I don't get confused with stuff. Whatever. Anyway, so this thing is equivalent. It's the same function, right? All we've done is push some symbols around and write it in a different way. Again, more coming on like why, but this is the standard form. Where these are the coefficients, A, B, and C, right? So like here, A is -1, B is 4, C is -7.
Seems a lot more confusing to write it in standard form than we do in whatever.
Well, so yeah, and generally we're not gonna like. So there's kind of two things going on. Like on one hand, this is just good practice of algebra skills, right? So we're doing it for that reason. It's nice to be able to go back and forth from one to the other sometimes, maybe. We're never gonna really have a lot of situations where you like have to go from one to the other, apart from kind of today where we're trying to get a feel for it. Because pretty much the things that you can do there, we're going to figure out ways that you can do them here as well. Okay, but mechanically, everybody okay with what we just did? Anything we need to talk about with the actual like algebra? Okay, so one, I wish I had a thing to point with things at. Here, I'll sign up on the sharing, kill myself. This, the vertex form thing. Oh, wait. The vertex form thing, here we go, is nice because we can look at it and read off that opens, which way? Down, and the vertex is 2, -3. Right, so I can get that just, no problem. Once you've done 4 or 5 of them, you'll have a feel for it too. So we can just read that off. That's nice. This is going to be easy to do some other stuff with, like solve equations and that kind of thing. A little easier to work with than that. Again, I know that's kind of the like delayed gratification thing that we're not going to see for a little bit, but like take my word. But I can't look at this and read off where it is, right? I can still tell that it opens down because of the negative coefficient here, but I can't just look at it and read off the vertex. We do have a thing that can help us with that. If you look at that first bullet point up at the top of the page. If a thing is in standard form, then we can get the vertex by doing this. I know this looks like more than it is. We can't really get too far into like why, because you need calculus to derive it, but basically this is the thing that we want to hang on to. I hate having to, tell you to just remember a thing, but this is going to be one of like 2 times that we got to just remember a thing. So the x coordinate is the opposite of b divided by 2a. That tells us where it is. The second part of that, the f of negative b over 2a, that's just finding the y that goes with it, right? That's just plugging it back into the function. So really this here, that's the only thing that we're trying to like, memorize or remember or whatever. Negative b over 2a. And again, by the time you do it 3 or 4 times, you'll have it memorized whether you want to or not. Find the vertex. So if I'm going to find the vertex from that standard form, what I know is that x is the opposite of b over 2a. So if I take b, which is 4, and a, which is -1, and set that up, negatives cancel, 4 over 2 is 2. So the x coordinate of the vertex is 2. Okay, that tells me where it happens. Now I want it as a point. So I just plug 2 in to the function. -4 plus 8. 4 minus 7. -1. What?
4 minus 7 is 11 plus b.
Yes. Wait, what? Hang on. Oh, right. No, I can't subtract. Yes, okay. Sorry, -4. No, plot. Hang on. You have calculators. Forget it. It's -3, right?
Wait.
-4 plus 8 is 4. 4 minus 7 is -3. Okay, go work, everybody. We did it. Feel we have a lot to be proud of that. A lot to be proud of there. So the vertex, it's math class, not arithmetic class. 2 -3, which is good. That's what we had before. We know that that's what the vertex ought to be, right? This is what finding the vertex would look like from a thing that's in standard form. So it's not quite as direct, right? I can't just like look at it and read it off, but it's not really that bad either. The calculation, again, assuming you have this thing handy, you can, find that fairly quickly. This is also kind of nice in like applications and stuff because A, B, and C might be kind of messy. It's a pain, as we'll see in a minute, to get from, to get back into that like vertex form. And also in applications and stuff, you might be dealing with numbers that are like way out here, right? Like your calculator shows you 10 to 10 by default. We might be dealing with stuff that's in like the tens of thousands. It's going to be hard to like just go find that kind of out of nowhere, right? But here you can do kind of a quick, straightforward little thing and get it. Okay. Everybody good so far? All right, take a look at number 2. G of x is x squared plus 6x plus 8. So it's in standard or vertex? Standard, right? Okay, x squared plus 6x plus 8, standard form. So A is 1, B is 6, and C is 8. Sign goes with it if any of them are negative. But I want you to take a minute and find the vertex and the axis of symmetry and the domain and range. And then, maybe think about how we would reverse what we did a minute ago. Okay, so the opposite of B over two A, B is six, A is one, so -6 over two, so -3. Okay, then plug -3 back in, back into the original function, so I get -3 squared plus 6 times -3 plus 8, so 9 minus 18 plus 8. I got -1. I understand if we're not feeling all that confident in my arithmetic now, but you also get -1.
Yeah.
Okay, cool. Yes. That's pretty good baseball. What's the axis of symmetry then? Shooting 3-pointers, that's pretty good there too.
Could get -3.
X equals -3, thank you.
Yeah.
Yes, because crouchy old man Thomas is gonna make a big deal about the equation thing. All right, what about the domain and range? Yep, all real numbers for the domain. Why -1 to infinity, to positive infinity? It's facing up, it's opening up. So -1 is the lowest point that it passes through, right? So -1 is where the range starts and then goes up from there. Good. Okay, cool. All right, everybody happy with that? Okay. All right, now this last part, rewriting it in vertex form by completing the square. So what we're trying to do is basically take what we have and what we did here a minute ago. We're trying to go from here and work backwards, right? So go from something like this to looking something like that. To do that, we have to use a method, a technique that we call, doggone it. Hang on. There we go. That we call completing the square. Notice I italicized that whole thing. It's, like all one phrase. That's what the method's called, completing the square. Basically, what we do is we take this function that we're dealing with. We're going to factor it, but we're not just going to stick to like normal factoring. We're going to factor it, but we're going to force it to act like a perfect square. It probably isn't a perfect square, so that's where the completing part comes in. We have to kind of make it work. So let me leave some room here. We'll come back to this in a second. Completing the square. So let's start by just looking at a thing that is a perfect square. Let's take x plus 3 squared and expand that. Well, squaring it means you take two copies of them and multiply them together, right? So that's x plus 3 times itself. How do you expand that?
Solve it up.
Mhm.
4.
Yeah. Everything hits everything else. We get x squared from the first terms plus 3x plus 3x again plus 9. Distributing both of those, or from FOIL if you want. And then we combine like terms. Okay. So that's what expanding a perfect square looks like. What if I wanted to color factor x squared plus 6x plus 9? How do you factor a thing like that? Three times 3 gives you 9, and 3 plus 3 gives you 6, right? So we split that middle term up into 3x and 3x, and then you can see the factors, right? If this is the first and the outer and the inner and the last parts of the product, then what the factors have to look like are x plus 3 and x plus 3. And since there are two of them, we just rolled those together and say x plus 3 squared. Which is good because we just did the same problem, just sort of backwards and forwards, right? So, okay, cool, like it, good that we ended up in the same place. What we're gonna do is use this same idea to deal with things like the one that we have right now that are not perfect squares. So keep all this in mind that because it's a perfect square, the factors are the same. Because the factors are the same, the outer and inner parts of that product look the same, right? Because you're talking about x plus 3 times itself. So when you do the outer part of the product and the inner part of the product, you get the same thing in both places. So if I'm going to try to do this with this thing, x squared plus 6x plus 8. If my goal is to do stuff so that I end up with x, plus something, I don't know what, squared, and maybe there's something else out here, but end up with that sort of perfect square like form, right? Because again, what I'm trying to do is make this look like that vertex form, as well as, figure this technique out. But how could we start? Does anybody see a way we could get into things, Brian? Okay. Okay. So you can factor this as x plus 4 times x plus 2, right? Check x squared plus 4x plus 2x plus 4x, so 6 plus 8. So it does factor like that. But we didn't end up with that sort of like perfect square thing that we were looking for, right? So that is factored correctly, but we haven't sort of done what we were trying to do, which is to like rewrite it in this, sort of vertex like shape where like this one by completing the square. Sounds like a good idea. Good thing to try and good thing to have in mind for sure, because we're going to have to do some factoring pretty soon. But specifically for completing the square, the whole thing relies on ending up with two factors where whatever's here is the same as whatever's there, right? Having identical factors. If those are going to be identical, it has to happen that this thing gets broken up, but it's got to get broken up in a kind of particular way. If the factors are going to be the same, what has to happen with that middle term? Maybe look at this where we were actually factoring a perfect square. What do you notice about that middle term and sort of where it comes from? They add together to give you 6, but it's not just anything that adds together to give you 6. It's 3 and 3, right? They're the same. These have to be the same to make these the same to make this a perfect square, right? Okay, so the way we kind of leverage ourselves into completing the square is to take that middle term and break it in half. Split middle term in half. That's the way we get into the thing. If you look at like a textbook explanation of this or something, it's going to say like find b over 2. So we split that middle term in half because I'm trying to force this thing to be a perfect square or to look like a perfect square, which would mean that the outer and inner parts of the product have to be the same because the factors are identical. All right, so we break that in half. Now I've got x squared plus 3x plus 3x. I'm going to put this 8 kind of off to the side there. Don't worry about the 8 for right now. It's there. It's not going anywhere. We're just not going to look at it for a little bit. X squared plus 3x plus 3x. Those look a lot like, and we can treat them a lot like, the first and outer and inner parts of a product of binomials, right? So if what I'm trying to do is figure out how to factor this so that the factors are identical, what would they have to look like to give us x squared here? Well, x times x, I guess I already filled that part in. To get 3x and 3x as the outer and inner parts, what would these have to look like? Plus 3 in both places, right? So that when I multiply this out, I get x squared plus 3x plus 3x. Okay, cool. What else do you get? Plus 9 at the end. The name of the thing that we're doing is completing the square, right? This is the square part. The completing part is that there's something missing. That's this. So that 9, that's like the last part of the product, right? That's the Olin foil. This stuff, we're grouping up and factoring, right? That's turning into this x plus 3 times x plus 3 or x plus 3 squared. But that 9 has to come from somewhere, right? I can't just like write a 9 down without changing things. Right now, this is different than all of the other things written up here because of that plus 9. So how do we fix it? Subtract 1. Oh, I think I see what you're saying. So I need a 9, right? Borrow the 9, which leaves left over minus 1 on the outside. That's what, yeah. So you can think about it as, if you want, you can think about it as like adding 9 to both sides, only we move them both over to the same side of the equation because we're treating it like a function. Or I usually just think about it as like borrowing, right? So 9 minus 9 is 0. So I haven't changed anything. I've just split 0 up into 9 and negative 9. And then I roll this in with the sort of leftover stuff out here. Now look at this. So we've got it in this like vertex form, right? Where we've got this perfect square factor with something outside. What's the vertex here? This plus 3 is shift to the left, so negative 3, negative 1. Oh, good. Okay, it's the same, right? This still opens up, still has the same shape, everything else. So that's completing the square. Sort of this process that we went through. Another way to do it, and this is what like a textbook is going to say, is take b divided by 2, square that, so you get b squared over 4, add and subtract that in. That gets you to the same place, but to me, it's sort of easier to think about like where things are actually coming from, and you get more out of it if you can see what's going on. But again, whatever makes sense for you. But so split the middle term in half. This is what I would call the like completing the step, complete the square. It's missing something. And then this minus 9 is adjusting or borrowing. And then once we have that, we just factor this stuff, which we've already kind of set up, like what the factors are going to look like if this is the first and outer and inner last parts of the product. And then whatever's left over outside is left over. That's our vertical shift. Okay. Questions about things? This is a technique. It's a whole thing. It's a thing that when it comes up in pre-cal,
I gotta remind you of pre-cal. When it comes in calculus, I gotta remind you of calculus. So this isn't a thing that like you see me do it once and you're like, oh, light bulb done, deal, now I'm good to go. It's a thing you have to do a few times to sort of get a feel for it. Of course, you get some practice in the homework and look at number 3 at the bottom of the page there. Do that for Thursday. On vertex, on the axis, symmetry, domain, and range. Try to complete the square. Everything there is even. So I would factor a 2 out and kind of hold on to it, do all the stuff, and just sort of leave that 2 alone for the right. All right, y'all good day. I'll see you Thursday.
Absence.